Okay, so thank you very much for the introduction. I very much appreciate it. I was going to start by sort of I had this funny conversation with the Canadian Revenue Agency the other day. They called me up and they're trying to figure out, okay, so what is it that you actually do? And it should be straightforward, but it wasn't quite so easy. And you know, if you look at my publications, this year alone, I had the opportunity to publish at a science journal regarding sort of flap structures. Then I published in the Integrative and Comparative Biology Journal. And I also got the chance to recently publish, we just got a paper accepted this week on the Engineering Journal, Materials and Design. So they, you know, said like, okay, well, that's teaching, that's great. So why are you buying so many materials? Like, what is all these expenses that you have? And they realized that, you know, I also build stuff, and I build student projects. I do some product design, I do a bit of marketing, and my practice in Shanghai has also been growing, and we have a number of projects going there. And yet I'm not licensed, which also makes the CRA more confused. And there isn't really anything, I would say there's nothing really particularly special about what I do, because I think we are all sort of in the same sort of mindset of looking at design and looking at things, looking at the world with a very kind of keen eye. So I think if you're like me, which I assume all of you guys computational designers and experts are, you look at this image and you might, you know, if you're like me, I start to look at it and I see a little bit of a building, and I see different layers, and I start to think of how I would script this. I think of it as a, you know, multi sort of system structure. I start to see grid lines. And that's not really too foreign. I mean, we do buildings that have all these sort of complexities. We have to model them. We have to kind of make and manage these interrelationships. And in any building, big or small, you know, understanding those functions between the geometry, the materials, and how they all kind of need to work together is sort of the core of what architecture is, that kind of deep material and geometry interdependence. Architecture, however, is an interesting sort of word, because when we look at biology, and I'll use the example here of the lobster, they have very specific spatial material functions in the way their materials work. And the lobster, as you use an example because you probably have all dealt with it, has very strong pinchers, very soft abdomen, and yet is the same material. It's actually functionally graded material that uses the same fibers and changes that orientation to precisely give different mechanical properties. That might seem, you know, you found it, but you don't know necessarily much about it, but you have also run into products, new products that are starting to integrate some of the same principles. If you look at shoes that now have fibers that start to create different grains of stiffness that are 3D printed, that start to integrate some of those properties, you're kind of looking at sort of the forefront of digital design and fabrication. Keep in mind, there's nothing new. I mean, we have Tinker Hatfield doing the Nike Air Max and bringing a lot of ideas about architecture, a lot of ideas about structure, directly into how things are made. But you don't have to make shoes. My point is, you know, even though product design is perhaps part of what we do, you don't have to be making shoes. You have to have the same challenges. In practice, we very commonly need to work with very different materials, very different functions, and we use digital design as a way to kind of understand that complexity. One of the challenges that I find is that if I come up with a great idea, and let's say I thought, oh, we know there's this biological organism that is really cool, has this cool box joint, and I go to a fabricator and say like, hey guys, I have this great idea. What would it take to do something? They will come back to me with something like this. They will have all these tools, all these issues, and all these challenges of how I cannot do it. And they will tell me also there's this long process to make them possible. And obviously they want to sell me things, products, they want to sell me software, they want to sell me machines. It's sort of the way we do it. But what the invitation I think I'm proposing is that if we think about the tools that we have to design and to make, and we think closely on how those can be directly integrated way we make things and the way that process is a seeming continuum, then we have a lot to offer. And this is the legacy from the Institute of Computational Design in Stuttgart, where I kind of studied and continue to develop my research as part of my PhD, where they take that information and they make it expressive and they make it part of the way things are made. Not only that, but I think they're continuing to be at the forefront of this research because they're progressively not only integrating the geometry, but also the way the multiple tools engage together, and the way that integration is making ever more complex and challenging structures possible. And that integration is, I think, the key sort of point I would like to come across, because when we look at this cell wall, this cell structure from wood, I also cannot see it without thinking of it as a vascular tissue capable of moving moisture, energy, is dependent on growth, it kind of functions as a very active structural system. And again, that's the same way we have to think about buildings, the same thing all of you think about buildings, and realize that energy flows, there are functional gradients of materials, there are all kinds of systems, living systems that are also integrated within our buildings. And looking at nature is really compelling, because we can look at that complexity and we can think of it as deficiencies, as challenges that need to be overcome, or we can work with it. We can actually look at them as inspirations and mechanisms to see how they're actually integrated and how our tools might enable it. So in the case of hygroscopic expansion, we can see that nature uses it to create the pine scale, which is one of the most effective seed dispersal mechanisms. Or we can look at the work of my colleague Stefan Reichert, which kind of worked to create this kind of simple mechanism that responds to humidity. As designers, computational designers, we start to expand how that complexity starts to allow for ever more engaging geometries, engaging sort of applications, engaging expressions of that design, and then how they might play a role in a building. So in this case of this project, this is a building that when the sun comes out, all the apertures open autonomously, and when the rain comes in or high moisture comes in, then they all close up. But that's still looking at materials that we find and principles that we try to kind of appropriate. But we can also even go deeper, and this is something where architects, engineers, designers are actually looking very closely, where what if we actually 3D print? What if we understand the spatial and formal and functional interrelations between how fibers, materials, and structures work, and we create new materials? Here you can see carbon fiber very precisely arranged at the microscopic level, then spatially graded to create essentially tissue, 3D printed tissue, that borrows some of that knowledge that we have from our own structures, combine it with structures from nature, and allows to create really unique materials. And this you're seeing it in engineering, you're seeing it in aerospace. In my sort of work, that kind of translates to taking wood, making it a synthetic mechanism, expanding the capacity that these things might have to create more complex geometries, to create different ways of engaging. And going back to nature in some way. So, because nature has these really compelling things with very compelling movement, but when we work with biologists, they understand how they work, they study it, but being able to take those ideas and translating them with materials, mechanics, and functional principles is the domain of architecture and design. And you can see here, for instance, the Lilium Casablanca, the flight trap, the Venus flytrap, or perhaps more architecture oriented, you know, a double curved dome that can actually open up. Some of my students might take some more playful approaches to these ideas and think about little robots that might move and do other kinds of things. Or we can think of a different way to make all together. So here, for instance, you see a 3D printed flat disc that if it's submerged in water, it actually reveals a high level of material complexity and formal complexity that would have been actually incredibly difficult to manufacture through any other mechanism. I'll tie this in very closely to the work we do with the students, because that's really what we try to drive across, that integration is key, no matter what small principle it might be. So here you see my student, former student, Sarah Falamarsi, who took just small pieces, cut them, and then start to see what that precise positioning, moving from the digital into the physical, allow her to do. And if we take that stance kind of very seriously, you can start to see a very broad spectrum of information that plays in, from the structural mechanical behavior to the really kind of architectural potential that it might have. My other student, recent student, Nima Karami, he's looking and expanding that work to actually include machine vision and neural networks to actually start to understand how we might actually be able to recycle some components and use some of that capacity to think at across the board between making, concept generation, and application. At the larger scale, talking about things that I make, We do some of this thing in our teaching as well by, for instance, looking at folded double curve elastic structure using some origami, understanding what those structures do, then expanding, for instance, into looking at what geodesic lines do, what kind of role they might play. One thing I will point out is that these projects are actually all built in the span of 3 days. So the workshop takes 2 days where we teach you how to use robots, and then we go in to make them. And I assure you that if I were to show this project to a fabricator in its digital form, even in a paper model, I were to tell them, hey, you know what, I want you to do this, I would not be looking at any less than 6 months. I would be waiting for a long time for quotes. And if I were to even go closer and say, look, what I want is a joint that is actually using dowels that are fixed in place. It will provide lateral rigidity to the entire structure. It will take forever. Like, it would just not be possible. This process and this capacity we have at Digital Designers is really the tool that would allow us to really be able to explore the formal and aesthetic potential that these projects do have, but also to make them feasible, to make them tangible. The last kind of quick project I'll show something in polymer, something in wood, but I also want to show some recent work in clay, because clay is also a material that is widely used in nature and is widely used in our practice, any kind of cementitious materials, and is now more prevalent. And one of the things we're looking at here is, or we're learning about it, because I think that's really the best way of thinking about design and fabrication, is the process of learning. It's trying to understand what their design potential is. Not only what their aesthetic potential is, but also how that material has unique behavior, and how that behavior might actually give us some new ways and new aesthetics that we haven't explored. So you can see here the work by 3 of my students, Isabel, Yiming, and Andrew, where they're, it's a 3D printed object, but that sort of expression of the 3D printed work starts to gain kind of its own language. I will wrap up with another project where we're trying to look at, you can see every project, we'll take one small principle and we expand it. And here you can see the integration of computational tool to modulate geometry, a material process that expresses something beyond what the geometry in itself express, and then now a project we're currently working on to actually then upscale and really explore and investigate what the architectural potential might be. In this case, a wall. Recently, we're also working in a sort of this facade system, this facade structure. And I'll show you an example of how this is now translated also into practice. So in China, maybe we don't have robots, but we have the same tools. We have computational design, we have material exploration. So here you can see a framework that was highly rationalized, that then is an interchange with a process of manual material behavior that then kind of creates a completely different form of expression for both the material, the space, and sort of the interrelationship between the two. Whew, sorry about that, I went a little bit up. I thank you very much for your attention and listening to us. I also invite you, I leave you with an invitation to reach out to us at the school, reach out to our students. The talent that is coming out of Waterloo is exceptional. And this engagement material is something that we're bringing to the forefront. Connection between digital, computation, and materialization as one integrative process.